Yes. So just to introduce myself, I am Anjan Sil. I am from India, and I'm a faculty from Indian Institute of Technology Roorkee. So there are several IITs or the Indian Institute of Technologies. We are from one part, so that is India called Uttarakhand area. There's Roorkee. I'm professor in Metallurgical and Materials Engineering Department, and we are interested in research in the energy storage materials. So to come to the why the energy storage, I'll take a brief movement why the energy storage is required. As we know, these fossil fuels, this is a traditionally preferred energy source, fossil fuel, carbon-based, petroleum-based, gas-based, those materials. But it is coming closely to the, will not say the end, but there's a gradual depletion of this thing. And second is it has got a, the effect on the environment and the human health, not only human health, any animal, any kind of the animate object has got this health problem with this. So therefore, we have to explore to the clean and renewable energies or the alternative like solar cell, wind power, then tidal energy kind of things. So if we have this, but whereas we try to explore these renewable energy sources, we have also certain limitations. What are those limitations? We can realize that it has got a geographical dependence because many places this light is very poor, light is not all the time. Like in some places, light is adequate. So there's a geographical dependence is there, climate sensitivity is there. Sometimes it's very cold, sometimes it's hot. So therefore, for an example of the solar cell activity can be limited to this. Then if we talk of the intermittent, say if we talk of, for example, the wind power, we need to tap the wind power. All the time wind is not there, wind is not blowing. The velocity of wind is very low. So therefore, this is not. So therefore, whenever this the maximum availability is there, we must tap the energy, but where to keep it? We need to store the energy. In order to store the energy and in order to beat this requirement of the unreliable round-the-clock energy supplied, we do. So therefore, we have to couple with the good energy storage material. That is why our research comes into play. So as we know, we are familiar with lithium-ion battery system. If we talk about the consumer electronics, if we talk about the grid energy, if we talk about the electric vehicles, this we know this electrochemical energy storage is very important. And certainly lithium-ion battery stands first, I must say, from the energy density point of view. But lithium has got a different limitations from the resources point of view and then cost point of view. So therefore, there are alternatives, and we are moving to the sodium-ion battery system because sodium has got a same chemistry. However, the size difference is there of the sodium-ion has got a larger size compared to lithium-ion. However, we can make it matchable, these things. So in this regard only, we made few attempts and then also some results. So this is a battery system. So one is the cathode and this is the anode, and in between we have the electrolyte. So as we know, this from cathode to anode when it goes, so we say there's a charging. So when once it is charging is done, so we have to use this battery, I mean to power this device. So we have to connect or we have to load this thing and this from anode to cathode. So this is charging part, this is discharging, charging, discharging, this is what is happening. In order to do that, energy storage is actually happening in the electrode side, not the electrolyte. So the electrodes have to be very good in the energy storage side. That means the capacity of electrodes should be very high. So in sodium-ion battery, electrode material, especially the anode material where we are focusing, is not graphite material is not used because of the size is larger than the lithium size. So therefore, hard carbon material is one of the material of the choice other than the oxide materials and other things. So in this regard, we had made few attempts. I will show the results, some of the results like hard carbon. This is one of the promising anode material. And then just to make familiarize that what is the important is, because this is called the discharging curve from this voltage is gradually with capacity goes this is maximum. And then we have a charging and discharging behavior. I'll show the results of now, if we have the minimum voltage of anode and the maximum voltage of cathode, we can have the high cell level voltage. between cathode and anode voltage difference is the cell level voltage. So this is where we are focusing on the anode material. So therefore, I am showing this anode material discharge curve. Then we'll show the cell level activity. I'll show the cell level activity. So we are interested in the materials part. I come from the materials engineering department. We are focusing on the materials aspect. We couple with this material developed through the electrochemical characterization in order to demonstrate the cell level activity, then finally to the battery level activity, and then industrial productions and those things. So one of the materials which has found a very good space, this bio-waste derived carbon material, which give the hard carbon based materials across the world, bio-waste derived materials, but still it has not been fully settled in the sense the standardization has yet to be done. So one of the attempt we did a P-skin material. Sorry. Yeah. One of the material, this is a P-skin material, this is one of discarded waste, has got no expenditure at all. And this material we tried to do converting into the carbonization process. Then we tried to do this electrochemical analysis, and those things were done. So basic scheme of this is the thing. Pyrolysis is done in the tubular furnace. Then the morphology, the honeycomb structure morphology has come. Then this carbon material will have to be converted into the slurry making and paste it into the onto the sheet of this aluminum foil, and then it is dried, and then this is inserted into the cell device, and then electrochemical charging discharging behavior studied. And before that, the material was tested with the thermal analysis by DTA and the TGA method and this, and find out what is the calcination temperature and this shape temperature, all those things. And then it has been done this XRD analysis. Why two different shown is this P-skin material contains this in situ, it contains the magnesium oxide as well as sodium chloride. From the source itself it comes. Now our target is to look at if the material containing sodium chloride and containing magnesium oxide both will act as a good template making material, how they behave and what are the phase differences and other things. Whereas if it is free from magnesium oxide, what difference it comes. So this was one of the targets. So such activity was performed, and and this is what the this thing pyrolysis process. If we have a soft material like the graphite, it gives the higher temperature 1000 plus, the graphitization takes place this. Whereas for the hard carbon, even if we go to 1000 plus degree centigrade, it is not a fully graphitized, it is gradually graphitizing, but that takes to very high. So therefore, it is non-graphitizable material. So it is a mixture of graphitic and non-graphitic, what we call the turbostatic graphitic. And then this material is actually used for the anode materials of sodium-ion battery. And this is developed. So two materials are tested. One is magnesium oxide, sodium chloride template-based material. And this is only because with acid washing, this magnesium oxide, this material was, one material was removed. And so therefore it is, this should be actually N. This is not Mn, this should be actually N. So now this is the synthesis of we have a hard carbon material, add carbon black, then PVDF binder, then disperse in NMP solvent. Then we have to mixer, we have to start it at 80 degrees centigrade for 2 hours. Then the homogeneous slurry is made, right? Now, some of the test results are shown. So when we talk about the, since it is a porous carbon, so porous carbon has to have the large surface area. So in order to measure the surface area, BET surface analysis was done. So this shows the relative pressure versus the absorbed nitrogen, this thing, and then pore volume, pore size versus the volume, pore size versus the volume of two materials. Please, I again point it out. One material is magnesium oxide, sodium chloride, both present templated material. Another material is devoid of magnesium oxide, only sodium oxide, sodium chloride present. So this is what two different type of materials were tested from there. Two different means hard carbon based on this. Then this shows the ACM, FEACM microscopy, this thing, just to look at the, just to see the porous structure with higher resolution this, so you can have the honeycomb structure. So this mesoporous solid helps the sodium storage and the easy movement of the sodium when it is in contact with the electrolyte. So this is the basic morphology of the structure, and this helps in the good mobility of the sodium. And this shows that TM and TM morphology, this material has got this material with carbon structure, this amorphous. Then if we look at very critically, we can look at this magnesium oxide crystalline phase is also present, and this is also present, the sodium chloride. And since this has no magnesium oxide, so only shows the sodium chloride. So it is a mixture of amorphous and crystalline, and only part of crystallinity is there. So in order to tune the sodium storage mechanism, so and control the sodium storage, and that shows the, this shows the what are the elemental disposition is there. Now we have performed the Raman spectroscopy just to see the disordered peak versus the graphitic peak, and then this ratio of two material, one material is this, second material is that. So therefore, two different material, there is a slight difference in the ID by IG ratio. And then we this XPS analysis shows this, what are the surface groups are present, like carbon-carbon, which is due to disordered carbon, and this is oxygen group present, carbon-oxygen group present, because presence of oxygen on the surface may tap the sodium, and then sodium will not be able to penetrate inside the structure, and then it will change the capacity of the material. So this is where all these studies were required, and this was conducted. Now, when we talk about the rate capability or the charging, this is cyclic voltammetry. This current versus voltage of this material, we have this first cycle, then we have a second cycle this, and the first cycle rate 1, then the second cycle, and then what is happening, we can notice that with respect to this number of cycles, this hump is gradually vanishing. So that means actually this hump comes from the EIS, that is a ACI, the solid interface layer, and then this oxygen group present on the surface. So these two, when the gradually oxygen group present is eliminating, so then this more smooth curve comes. So that is the observation was made by this, and then what is the diffusive control and the slope control, this thing, this diffusion and the slope. So this was, and this comes from the, what is the capacitance from the slope plateau behavior, and what is the capacitance from comes from the slope behavior. These were estimated and tried to plot here, and then Coulombic efficiency and this thing, as well as this at different current rate. If we do this thing, how the capacity varies, and it is fully reversible. When we start from this current rate to come back to that current rate, it almost equalize, not exactly, but it goes like this. So all these testing were done in order to make the material to be used as a good anode material. So this is the how they estimate this diffusive control part versus the this non-diffusive control part. So that part was estimated, and this is where these things are done. Then when you talk about the this thing, cyclic voltammetry, this again current voltage for different scan rate. If we talk about the different scan rate, so this is where it's given. And for different scan rate, what is the ratio between these two? One is the capacitive part, another is the diffusive. One part is the just on the surface it settles, another is the diffusive control, so it takes time. So therefore, this is very important to look at. And what is the ratio? If we go from the very low scan rate, we have a good diffusive part. At least percentage of diffusive part is 30% or so. When you have a high scan rate, so you have a diffusive part is only 10%. So therefore, it is not getting adequate time to go inside and coming back. So this is what to just to observe. Then we have the plot. This is the plot of the log of rate versus this thing. And this is again the conductivity measurement. So for two materials, conductivity by EIS measurement, electrochemical impedance spectroscopy studies. And then this what we try to find out that which one has got a higher conductivity. And then what happens that because the cells have to be tested for large number of cycles. So here after 200 250 cycles, when we look at the morphology, we can find this, there are cracks formation, indicative of the crack formation is there. Whereas this material does not show any evidence of the crack formation. So from the application point of view or from the use point of view, this is very important to look at that what is morphological changes is happening with number of cycles. First cycle, 2 cycle, 5 cycle is fine. But as we go hundreds of cycles, then how changes in morphology is taking place, because it has to sustain the this capacity behavior. So therefore, this is very important to see. So that's what was observed. Sorry. Then when you compare this result with the previously researchers' work and this, some of the references were given. So if we talk on this, we find this is the capacity at 20 milliampere hour per gram current rate, which is relatively high, not very high, relatively high to sustain. So that gives about 240, around 240, this thing, specific capacity milliampere hour per gram. And this is what is the range is given. And this material was tested first time. And then we are still in progress with this work. This is the present work. We are still in progress with the work with some more studies. And now coming to the conclusions, I would say that 3D honeycomb structure carbon was synthesized from the pea skin waste by a simple single-step pyrolysis method. Carbonization temperature is relatively low, 750 degrees centigrade temperature only. And then this material shows an excellent performance with reversible, although 50% capacity after 250 cycles and 99% Coulombic efficiencies were retained. And then this was attributed to the surface area, optimum pore size, mesopore size, of course, created by this template method. And the less surface oxygen functional group. More surface oxygen functional group means more capture of sodium. And less means less capture of sodium. More sodium is available for the capacity point of view. So that usage, so that has been tested and we can optimize in future work. And then we can talk on the sodium chloride template in this sample helps in this mesopore creation, resulting in the shortening of the diffusion path, because this is also important. If we have a shorter path of the diffusion, we have a good rate control. We have a good rate. And faster rate is very important in the sense that when we talk of the electric vehicle charging and discharging, we cannot wait for the hours together. The thing has to be very fast charge and very fast, very fast charging should take place. So therefore, rate control is one of the very important factors of this kind of ion energy storage material like sodium-ion battery. In future, we have other types of battery, potassium-ion battery, zinc-air battery, aluminum-air battery, and those things. Of course, we are moving through the lithium-ion battery system now. And reduction of the charge transfer impedance. Charge transfer resistance has to be as minimum as possible. Then what will happen between electrode and electrolyte? If the charge transfer resistance is very high, then it will lose a lot of energy while crossing it. So that should be minimum. So this is what is the study, and we have been successful to some extent. Moreover, this mesoporous acts as a reservoir of this thing. So because of the pore volume is more, so the more and more sodium is the active ion. So the more and more containment of the atom, ions will be there. So this is this thing. Then the synthesis is low temperature, exemplary electrochemical performance, makes it simple, it is strong, cost effective, we have to see. And the scalability, when you talk about the industrial application scalability, in the sense that we need to make the material in a bigger quantity with a low cost material. So this is possible with the bio-waste derived. and that to kind of be discarded waste material. So this was one of the criteria we can think of this thing. And there are few references. We have referred while performing this work, and then we are coming to our own work. And lastly, thank you very much.
Thank you very much.
Okay.